Imagine a chaotic pile of objects, books, numbers, planets, ideas. Now, imagine drawing a circle around just the books. You've just created a set. They're all sets. Welcome to our deep dive into the fundamentals of set theory. Sets are one of the most basic building blocks of modern mathematics. In this video, we're going to cover everything you need to know to get started. We'll start with the absolute basics, what a set is and how to write them. Then we'll explore the different types of sets, like empty sets, infinite sets, and subsets. After that, we'll get into the really fun part, set operations, how to combine and change sets using things like unions, intersections, and complements. Finally, we'll see how to apply these rules to solve practical problems. Ready? Let's get started. So, what is a set? Formally, a set is a collection of well-defined objects. That phrase, well-defined, is the most important part. It means we have to be able to tell with 100% certainty whether an object belongs to the set or not. For example, the set of vowels in the English alphabet is well-defined. We know it's A, E, I, O, U. If I ask you, is B in this set, you can definitively say no. If I ask, is E in this set, you can say yes. But what about the set of beautiful cars, or the set of hard-working students? These are not well-defined sets. Why? Because the words beautiful and hard-working are subjective. What one person finds beautiful, another might not. There's no clear objective rule for membership. Now, let's talk about notation. We use capital letters like A, B, C to name the sets. We use small letters like A, B, C to represent the elements inside the set. To show that an element belongs to a set, we use this Greek symbol, epsilon, and it means is an element of or belongs to. We would read this as A belongs to set A. And if an element doesn't belong, we just put a slash through the symbol. This is read as D does not belong to set A. Simple as that. Okay, so we know what a set is. Now, how do we actually describe one? There are three main methods. First is the verbal method. This is just using a plain English statement to describe the elements. Second, we have the listing methods. This is where we explicitly write out the elements inside set braces. This method has two flavors. One, the complete listing method, also called the roster method. This is when you can easily list all the elements. For example, the set of the first three even numbers. Two, the partial listing method. We use this when it's impossible or just too tedious to write every element, but the pattern is obvious. We use ellipsis, or three dots, to mean and so on. For example, the set of whole numbers from 1 to 99. And third, we have the set builder method. This one is the most mathematical and powerful. It describes the set by stating the property or condition that all its members must satisfy. It looks a little intimidating at first, but it has a simple structure. Let's break this down. A equals squiggly brackets means A is the set, X is our representative element. We're saying A is the set of all element X. The vertical line, or sometimes a colon, means such that. And after the line is the condition, this means X is a natural number and X is less than 11. So this is just a very precise way of writing the set 1 through 10. Now let's get into the different types of sets you'll encounter. First, the empty set. This is a set that contains nothing, 0 elements. It's also called the void set or null set, We write it with empty braces or this special symbol. An example, the set of all living dinosaurs. There aren't any, so the set is empty. Next, finite sets and infinite sets. This is just like it sounds. A finite set has a definite, limited number of elements. The set 1, 2, 3 is finite. The number of elements in a set A is written as n of A, so here n of A equals 3. An infinite set is, well, not finite. It goes on forever. The set of all natural numbers, 1, 2, 3, ... is a classic example. Now for two that often get confused, equal sets versus equivalent sets. Equal sets have exactly the same elements. The order doesn't matter. These two sets are equal. Equivalent sets just have the same number of elements. These sets are not equal because their elements are different, but they are equivalent because they both have 3 elements. Next, the universal set, written with a capital U. This is the set of everything for the problem you are currently working on. If you're talking about numbers, the universal set might be all integers. If you're talking about students, it might be all students at a specific school. For example, if we have set A as 2, 4, 6 and set B as 1, 3, 5, then the universal set U is formed by combining all unique elements from A and B, resulting in U equals 1, 2, 3, 4, 5, 6. And finally, a really big concept: subsets and proper subsets. A set A is a subset of set B if every element of A is also an element of B. We write it with this symbol. For example, if A equals 1, 2, and B equals 1, 2, 3, then A is a subset of B. There are 2 key rules. 1. The empty set is a subset of every set. 2. Every set is a subset of itself, so B is a subset of B. A moment ago, we looked at subset, which means I am fully contained in you or I am equal to you. Now let's look closely at what a proper subset is. And notice the symbol, the line underneath is gone. For a set A to be called a proper subset of set B, it must meet 2 critical conditions. Condition 1, A must be a subset of B. This means every element in A must also be found in B. This is mandatory. Condition 2, A must not be equal to B. In plain English, a proper subset is like saying, I, set A, am completely inside you, set B, but you are bigger than me. B must have at least one element that A does not. Let's examine our example closely. A equals 1, 2, and B equals 1, 2, 3. Let's check the 2 conditions. Condition 1, is A a subset of B? Yes, 1 and 2 are both found in set B. The first condition is met. Condition 2, is A equal to B? No, B contains 3 as an extra element. The second condition is also met. Since it meets both conditions, we can say with certainty that A is a proper subset of B. Now let's look at this question, is B a proper subset of itself? Let's check. Condition 1, is B a subset of B? Yes, as we said before, every set is a subset of itself. Condition 2, is B not equal to B? This is false. B is perfectly equal to itself. Because it fails the second condition, B is not a proper subset of itself. It is just a subset, but not a proper subset. Now for the fun trick, counting them. Let's say a set has n elements. For example, if B equals 1, 2, 3, then n equals 3. What is the total number of subsets for this set? The formula is 2 to the power of n. For our example, 2 to the power of 3, which is 2 times 2 times 2, equals 8 total subsets. They are So then, what is the number of proper subsets? A proper subset is one that is not equal to the set itself. Out of that total of 2 to the power of n subsets, there is only one that isn't proper, and that is the set itself. In our example, 1, 2, 3. Therefore, to find the number of proper subsets, all we have to do is subtract that one set, the set itself, from the total count of 2 to the power of n subsets. So the formula becomes 2 to the power of n minus 1. In our example, 2 to the power of 3 minus 1 equals 7. This means set B has 7 proper subsets. Now we get to the really powerful part of set theory. So far, we've just been defining and describing sets. Now we're going to do things with them. We can perform operations on sets to create new, different sets. This is just like in basic arithmetic, where you take two numbers like 2 and 3, apply an operation like plus, and get a brand new number, 5. With sets, we'll take two sets, say A and B, apply an operation like union, and get a brand new set. And the best way to visualize all of this is with Venn diagrams. You've definitely seen these before. A Venn diagram is a simple drawing that shows the relationship between sets. Let's break down this picture because it's our home base for the next few minutes. This outer box, or rectangle, represents the universal set, U. This is our universe for the problem. It contains everything we are currently talking about. These circles represent our sets, A and B. They live inside this universe. The most important part is how they're drawn. This overlapping region in the middle represents all the elements that are in both set A and B at the same time. This part of circle A that doesn't overlap is for elements that are only in A, and this part of circle B that doesn't overlap is for elements only in B. Even the space outside the circles but inside the box is important. Those are the elements in the universe that are in neither A nor B. This one simple diagram lets us see every possible relationship. For our examples, let's use these two sets. Set A equals 1, 2, 3. Set B equals 3, 4, 5. And we'll say our universal set U equals 1, 2, 3, 4, 5, 6. First operation, union. The symbol is U. The union of A and B, written A union B, is the set of all elements that are in set A, or in set B, or in both. When you see union, think combine, or everything. It's like taking both sets and dumping them into one giant new set. In the Venn diagram, the union is the entire shaded area of both circles combined. Example, with our sets A and B, what is A union B? We just combine them. We get 1, 2, 3, 4, and 5. Notice we only write 3 once. Sets don't care about repeats. A union B is equal to 1, 2, 3, 4, and 5. Second operation, intersection. The symbol is N. The intersection of A and B, written A intersection B, is the set of elements that are in both A and B at the same time. When you see intersection, think common ground or overlap. It's like taking both sets and dumping them into one giant new set. Visually, the intersection is only this small shared piece in the middle where the two circles cross. Example, with our sets A and B, what is A intersection B? What element is in both sets? Just the number 3. A intersection B is equal to 3. Third, complement. This is written with a prime symbol, like A prime. The complement is the not operation. It's everything that isn't in the set, but is still inside the universe U. So the complement of A is every element outside of A. Example, A is equal to 1, 2, 3, and our universe U is equal to 1, 2, 3, 6. What is A complement? It's everything in U that is not in A. So we remove 1, 2, and 3 from the universe. What's left? 6. A prime is equal to 6. Fourth, difference. This is written just like subtraction, A minus B. This means exactly what you think it means. A take away B. The result is the set of all elements that are in A but not in B. You start with everything in A, and then you remove anything that B can also claim. Visually, this is the crescent moon shape of A. Example, with our sets A and B, what is A minus B? We start with A, 1, 2, 3. Then we look at B and remove any of its elements from A. B has a 3, so we remove 3 from A. What's left? 1 and 2. A minus B equals 1, 2. Fifth, symmetric difference. The symbol is a delta. It's the set of elements that are in A or B, but not in both. It's everything except the intersection. Visually, it's the two crescent moons combined. Example, with our sets A and B, what is A delta B? We want the parts that are only in A, which we just found is 1, 2, and the parts that are only in B, which we found is 4, 5. Then we unite them. A delta B equals 1, 2, 4, 5. An easier way, it's the union 1, 2, 3, 4, 5 minus the intersection 3. And last, the Cartesian product. This is written with a time symbol, and it is very different. It gives us a new set of ordered pairs. This operation is about finding all possible combinations between the two sets, where the order matters. Example, let's use a simpler A for this one. A equals 1, 2, and B equals A, B. To find A times B, you take the first element of A, which is 1, and pair it with every element in B. That gives us 1, A and 1, B. Then you take the second element of A, which is 2, and pair it with every element in B. That gives us 2, A and 2, B. You put all those new pairs into a set. Now, what about B times A? This time we start with B. Take the first element of B, which is A, and pair it with every element in A. That gives us A, 1 and A, 2. Then take the second element of B, which is B, and pair it with every element in A. That gives us B, 1 and B, 2. Now look closely. Is the pair 1, A the same as A, 1? No. In ordered pairs, the order matters. Because the pairs are different, the sets are different. This means that, in general, A times B is not equal to B times A. This operation is not commutative. This concept is fundamental. It's the basis for the Cartesian coordinate system, your standard XY graph. Think of set A as all the x values and set B as all the y values. The Cartesian product, A times B, is the set of all possible x, y points on the graph. It's how we get from a 1D line to a 2D plane. We will now discuss an additional highly significant topic: disjoint sets. Two sets are called disjoint if they are completely separate, meaning they have no elements in common. The mathematical way to say this is that their intersection is the empty set. A perfect, simple example is, let set A equal the set of the first even numbers. Let set B equal the set of the first odd numbers. What is A intersection B? What do they have in common? Absolutely nothing. Their intersection is the empty set, so we can say that sets A and B are disjoint. Visually, it's the easiest Venn diagram to draw. There's no overlap. Next are De Morgan's laws. These are two of the most powerful rules in set theory. They show us how to combine complements, unions, and intersections. They are fantastic for simplifying complex logic. There are two laws. Let's look at the first one. Law 1, the complement of a union. This looks intimidating, so let's break it down. The left side, A union B prime, means first find the union of A and B, then find the complement, everything outside that shaded union. The right side, A prime intersection B prime, means first find the complement of A, everything outside A, then find the complement of B, everything outside B. Finally, find the intersection of those two new areas. So, what is outside A and also outside B? It's the same exact region, everything in the universe box except the circles. Law 2, the complement of an intersection. This is the second law. The left side, A intersection B prime, means first find the intersection of A and B, the middle overlap, then find the complement, everything except that tiny middle part. The right side, A prime union B prime, means first find the complement of A, everything outside A, then find the complement of B, everything outside B, finally find the union of those two areas, combine everything. If you shade everything outside A and also shade everything outside B, the only part you've left unshaded is that middle intersection. So, how do we use this in the real world? One of the most common applications is in counting. Let's say you have two finite sets, A and B. How many elements are in their union? N of A union B. Your first guess might be to just add them, n of A plus n of B, which is 10 plus 10. But what about the intersection? If we just add A and B, we've counted the elements in the overlap twice. To fix this, we have to subtract the intersection one time. This gives us the famous principle of inclusion-exclusion for two sets. N of A union B equals n of A plus n of B minus n of A intersection B. For example, in a group, 12 people like coffee, n of C, and 8 people like tea, n of T. 5 people like both, n of C intersection T equals 5. How many people like coffee or tea? We just use the formula, 12 plus 8 minus 5 equals 15. There are 15 people who like at least one of the drinks. And of course, if the sets are disjoint, meaning no one likes both, then n of C intersection T equals 0. The formula simplifies to just n of C union t equals n of c plus n of t. So we've drawn our boundaries and defined our elements. We covered the types of sets, how to operate on them, and how to use them to solve real problems. Like we said at the start, these are the building blocks. Whether you're going into probability, logic, or computer science, what you learned today is the foundation for everything coming next. Make sure to practice those operations, and if you have questions, drop them in the comments below. I'll see you in the next video. Class dismissed.